Welcome to This Explainer. Today, we're taking a step into the most fundamental kitchen in the universe, the chemistry lab. Now, it is incredibly easy to look at chemical equations and see absolutely nothing but a jumble of confusing math and strange symbols. But what if I told you that they're actually just logical, highly scalable recipes? In this explainer, we're going to see how chemistry is less about abstract math and a lot more about understanding the exact blueprints that build our entire physical universe. To do this, here's our agenda for today. First, we'll look at the chemical recipe itself. Then, we'll classify our different reactions. After that, we'll learn how to scale our recipes up, figure out our real-world yields, and finally, dive into quantitative analysis. Let's get cooking! All right, Section 1, the chemical recipe, building the blueprint. The most foundational concept you need to grasp here is that a chemical equation is really just a blueprint. It tells you exactly what you're starting with and exactly what you're going to make. You can see this blueprint in action right here as a molecular equation. On the left side, we have our reactants, one methane molecule and two oxygen molecules. Think of these as your raw ingredients. That arrow in the middle, that acts like our oven, showing a transformation taking place. And on the right side, we get our products, carbon dioxide and water. Bonds are broken and reformed, just like raw materials becoming a finished, baked meal. So, the absolutely crucial point here is that equal numbers of atoms for each element have to be represented on both sides of that arrow. I mean, think about it. You can't bake a cake with missing ingredients, and you certainly can't create a cake out of thin air, right? The universe strictly follows the law of conservation of matter, and this is exactly why we have to balance equations using coefficients. The math has to perfectly reflect the reality that matter is never created or destroyed. It's just rearranged. Moving on to Section 2, classifying chemical reactions, or the cooking methods of chemistry. Now that we have our basic recipe down, let's explore our cooking methods, which are basically just common patterns of reactivity. First up is the precipitation reaction. This happens when dissolved substances react to form one or more solid products. Now, to track exactly what changes, chemists will often write a total ionic equation to show all the dissolved ions, and then they'll simplify it down into a net ionic equation. That just highlights the specific ions that actually form the solid. I know, it sounds super industrial, but these reactions are incredibly common in nature. They're responsible for the breathtaking formation of ocean coral reefs, and, well, on a slightly less pleasant note, they're exactly how painful kidney stones form. Just look at this. This is the sheer visual proof of a precipitation reaction in action. We've mixed solutions containing lead-2 ions and iodide ions. Both of them started as clear liquids, but the exact moment they meet, they form this striking, bright yellow solid precipitate of lead-2 iodide that literally just falls out of the solution. It totally looks like magic, but it's really just the predictable rules of solubility at work. Our second cooking method is the acid-base reaction. At its core, this is simply a reaction where a hydrogen ion, NH+, is transferred from one chemical species to another. And let me tell you, these reactions are absolutely vital. They dictate the complex chemical transformations taking place within your very own cells right now, and they're used on a massive industrial scale to produce the fertilizers that help feed the entire world. We round out our classifications with oxidation reduction, or redox reactions. So instead of transferring a hydrogen ion, redox reactions involve the transfer of electrons between species. Now, because balancing that electron transfer can get pretty complicated, especially in aqueous media where water and other ions decide to get involved, scientists use a highly systematic, step-by-step process called the half-reaction method. This lets them balance these specific equations without, completely losing their minds. Section 3, stoichiometry, scaling the recipe from microscopic atoms to macroscopic grams. Okay, let's transition from simply knowing our ingredients and reaction types to actually crunching the numbers. This introduces us to stoichiometry. It's a big word, but it's really just the process of scaling our recipe from microscopic single atoms up to macroscopic grams. To avoid getting overwhelmed by the math, you literally just follow these 3 simple steps to convert between any amount of reactants and products. Step 1, convert your starting mass into moles. Step 2, use the stoichiometric factor, which is just the ratio from your balanced equation. And step 3, convert those moles back into your target mass. That's the whole shebang. This graphic shows the absolute heart of the process. Once you have the moles of your starting substance, let's say we're using propane, you simply look at the coefficients in your balanced equation. That ratio gives you your stoichiometric factor, allowing you to cross the bridge, so to speak, and calculate exactly how many moles of carbon dioxide you're going to produce. Building on that last slide, here is the complete picture. This flowchart maps out exactly how scientists scale things up in the lab. You weigh your reactant in grams, you use its molar mass to find the moles, you apply that stoichiometric factor from your balanced recipe, and then you use the molar mass of the product to find out exactly how many grams of product you'll yield. It is such an elegant, foolproof system.
Section 4. Real-world reaction yields. What happens when ingredients run out?
Well, here is where we hit reality. In a real lab, we almost never have perfectly stoichiometric, exact amounts of every single ingredient. So what actually happens to our chemical reaction when our recipe isn't perfect? Like, what happens when one ingredient runs out way before the others do? This brings us to a super crucial concept, the limiting reactant. Let's use a simple sandwich analogy to explain this. Say our recipe is 2 slices of bread plus 1 slice of cheese equals 1 sandwich. Now imagine we're provided with 28 slices of bread, but only 11 slices of cheese. Well, because we only have 11 slices of cheese, we can only make 11 sandwiches. The cheese is our limiting reactant. It completely dictates and stops the entire sandwich-making process, leaving us with 6 slices of excess bread. Believe it or not, chemistry works the exact same way.
This leads us directly into comparing our yields. The theoretical yield is what the flawless math from our stoichiometry promises we can make. But the actual yield? Well, that's what we physically get in practice. Real life happens. Side reactions occur, material gets stuck to the side of the beaker, or reactions just simply don't finish. The physical reality of the lab means our actual yield is almost always lower, giving us what we call our percent yield.
Finally, Section 5, quantitative chemical analysis, which is basically quality control in the lab. So how do scientists take all of these concepts, the recipes, the balancing, the stoichiometry, the yields, and actively measure exactly what they've created? They use quantitative chemical analysis. One of the most famous methods for this is titration analysis. This is where we slowly add a known solution, called a titrant, from a burette down into a sample with an unknown concentration, called the analyte. We just wait for a visual change, like a color indicator suddenly turning pink, to tell us the reaction is complete. Fun fact for you, back in the 18th century, people used an early version of this exact method to test the strength of vinegar by adding potassium carbonate until the bubbling stopped. Another really fantastic method is gravimetric analysis. So instead of measuring liquid volumes, we force a change of state, like intentionally causing a precipitation reaction. Then we literally filter out the solid precipitate, kind of like this bright orange one you're seeing, dry it super carefully, and weigh it. By combining the mass of the solid with our good old stoichiometric ratios, we can calculate the exact chemical makeup of the original sample. And that brings us to the ultimate question. How does mastering these microscopic molecular recipes allow us to actually engineer our macro world? Well, because once you understand that every chemical reaction is just a strictly balanced recipe, you realize that these foundational stoichiometric ratios govern the entire physical universe around us. From synthesizing life-saving medicines to formulating the exact rocket fuel yields needed to explore distant planets, chemistry really is the ultimate recipe book of reality. I hope this explainer has sparked your curiosity to go out and learn more about the brilliant blueprints all around us.